Okay, so in the previous classes we were discussing we started with the linear system with a brief introduction, and then why why the linear algebra plays a significant role in the matrix computation. That's what we discussed, right? And then after we went for the vector spaces, just a brief introduction, and the rank nullity theorem, that after the discussion between the connection of the subspaces of a matrix. So there were four subspaces of the matrix which were defined: um, column space, um, range space, and which are both the same, and then this row space and um, row space of A transpose and column space of A transpose. So basically there are four subspaces: column space of a matrix A, column space of A transpose, row space of a matrix A, and row space of A transpose, right? And then along with that there was one more important subspace which was also defined, which was this null space of the matrix A, right? Fine. And then after we discuss okay, there are some issues. Then after we discuss inner product space. That inner product space is basically um, every um, every vector space which is equivalent to the inner product space is having the can will be having will be having the measures of angle as well as the measures of the distance, right? So not all vector spaces have this measure of angle and the distance, right? So it helps us in defining the similarity or dissimilarity um, between the vectors belong to that vector space, right? So we then before that we define this rank nullity theorem, and I gave you some homework exercise also, that how the dimension of the range space of A will be same as the dimension of the range space of A transpose, right? So this was just a brief introduction we gave, and then we move to this eigenvalues and eigenvectors, right? So we briefly define this eigenvalues and we secondly define this eigenvalues and eigenvectors by considering a matrix A, square matrix A. Then we said that eigenvalue lambda in the real field domain uh, will will be associated with A by this equation: AU is equals to lambda U, right? And then we give some description that the corresponding vector U will be called as the eigenvector, and this is that vector, this is that direction in which when it gets operated by the matrix A, it is just gets scaled up by a factor of lambda, right? Fine, assuming that U is of unit magnitude. So in the standard notation, the U vector U is considered of the unit magnitude, right? And this is a non-zero vector. And then based on that, we define this characteristic equation. So it's a very important equation, um, as it helps in finding out the different roots of lambda, and we'll see one by one that what its various applications in the domain of matrix algebra and the machine learning is, right? So so um, moving further, so okay, there are certain issues. Okay, let me rectify it. Yeah. So um, let's see that how let's see that why this what actually lambda does. Um, so lambda basically makes this matrix lambda I n cross n minus a singular matrix, right? Because the right hand side is 0, right? So it makes it a singular matrix, fine. So it means that it possesses it possesses non-trivial null space. It possesses non-trivial null space, right? So so what does this imply? So it implies that u u lies in the null space of lambda in cross n minus a matrix, right? Fine. So what next? So lambda can be characterized as as the real or complex numbers based on which field we are considering. Complex numbers which satisfies this polynomial, the characteristic polynomial, right? Determinant lambda in cross n minus a, right, equal to 0. So one will get a characteristic polynomial, fine, by solving it. So this is called as the characteristic polynomial. Characteristic polynomial of degree n, fine. So that's a very important notion, is this one. Fine. Okay. So now next thing is the symmetric matrices, fine. Matrices, fine. So what are symmetric matrices? So for the symmetric matrix, symmetric square matrix, A will be equal to A transpose. Transpose of A will be same as A, right? Fine. So now let's consider some properties actually to the symmetric matrix. Suppose lambda is an eigen value. Okay, let's discuss this a bit later. I think it will be a bit early to discuss about this. So before that, let me give you some examples of symmetric matrices, so which you have already seen. So let's remove this first. Let's have some examples. So we'll just be dealing with the square matrices, right? Here this A will always be belonging to um, over a real field, means its elements will be real numbers, right, and will be a square matrix, right? So examples will be, so examples can be adjacency matrix, for an undirected graph, right?